Hi everyone. Today we are going to build a reinforcement learning agent that can play the popular game of tic-tac-toe. This problem is described really well in the Bible of reinforcement learning by Sutton and Barto. I'm talking about section 1.5 in the book. And then we are going to walk through a code today, a Python code, which actually builds a reinforcement learning that trains and plays this game. And then we will also be covering a scenario described in example 1.1 of this book. So exercise 1.1. So yeah, we'll be covering this also as part of the video. So without further ado, let's jump directly into the code. So I have this notebook ready. Um, the method that we're going to use today is the temporal difference learning, right? So what we are going to essentially do is we will treat each board configuration as a state. Every combination of XO that can exist on a tic-tac-toe is to be treated as a state, as a discrete state. We will try and learn a value of that state. Uh, the state function, right? Using the state functions. And then these are nothing but probabilities of the player winning when at that state, right? So our player will be called X. So the main player is the player playing X. And then we'll be competing against the player that plays O. And then once we know these values, we will keep on updating these values as part of temporal difference learning, right? So yeah, there is no neural network, no min-max algorithm. We are just working with a table of beliefs that gets better with experience, right? So we import necessary libraries here, and the first and foremost thing that we do when we articulate a reinforcement learning problem into mathematics, using mathematics is um, we define the environment, right? And when I say defining an environment, it means we define the state, we define the legal actions, we define how actions change with the state, and then we also define when an episode ends, basically the terminal states, right? So I do this here, right? So I'm defining the state, I'm defining the legal actions available, I'm defining how actions change the state, and I'm also defining the how the episode ends. So basically, the terminal states. And it is noteworthy that so we know that a player can either win, lose, or end the match in a draw, right? But it is noteworthy here that there are only 8 possible combinations where a player will win, right? So for a player to win, 3 x's should fall consecutively, right? So when you assign indexes to each box in a tic-tac-toe, so let's say if you assign indexes of position to each box in a tic-tac-toe, let's say this is 0, this is 1, this is 2, this is 3, 4, 5, 6, 7, 8. So there will be win situations only when X is available in these positions, right? So what I'm trying to say is there are only 8 combinations where a victory is possible, right? Otherwise, the match will end in a draw or loss. Um, okay, so we create a dictionary to collect value functions, and for a state that is not explored yet, we assume that the probability of win and loss is equal there. So we give it an initial value of 0.5. So this is also listed in the book. Um, I quote it. So we set the initial values of all other states to 0.5, representing a guess that we have a 50% chance of winning, right? So we initialize unseen states with a neutral 50% win probability. Now we define a function of how the agent will choose moves, right? Out of all the options available to it, which move is it going to take, right? So right, so we can have two strategies, right? So the agent can either explore or exploit, right? So we define an epsilon or 0.1, meaning 10% chances, 10% moves that the agent will be taking will be exploratory, right? So it will try new avenues, it will try new things, try new configurations of the board. And 90% time it will be taking it will be exploiting what it already knows, right? So it will be taking those actions where state value function is maximum, right? So this is essentially what is happening here. So it is, in the end, it is choosing the index, basically a position where the state value is the maximum, right? Yes. So mathematically, the update is happening using this equation, right? So V of st is updated by, or updated as, V of st plus alpha times this term, right? So alpha is the learning factor here, learning ratio, learning factor, yeah. So a short note on TD learning. So TD0 basically learns from the very next state, as you know, right? TD lambda is something that blends information from many future steps using a parameter called lambda. And then you have Monte Carlo, which is uh, also seen as TD1, right? Now, this is where we train our agent, right? So let's say we train on 50,000 episodes. You can choose to train it on more, but I think for a problem statement that we have for tic-tac-toe, these are enough. We choose an epsilon of 0.1, our alpha is 0.1. So what we're doing here is we're choosing a move for x. So x is always starting the game. So x chooses a move. The environment plays the move. Basically, environment is updated. The next state is chosen, and the trajectory is appended. So whatever the state we arrive at after taking the move is appended to the trajectory of x. Then what we're doing here is we're checking for the terminal state. Have we arrived at a terminal state? Is there a winner? If not, if yes, break. If not, continue. So, and then O plays, and then we again check for result. It is noteworthy that O is playing uh, as a random opponent. So so the choices of O is completely random, right? So it just basically looks at all the available moves and it will just randomly pick one. But X, on the other hand, is a smart player, right? So we are playing as X, and we have some exploration and some exploitation going on there, right? So cool. And then yes, this part of code is really noteworthy. So what is happening here in the backup loop after each game is, so whenever an episode ends, this code will run 50,000 times, right? So every time this code finishes, we will have a final state. We just, whenever we finish a game, the final board position already has its correct value. So it will either be 1 or 0. 1 is when if x1, or 0 is otherwise, right? So what we do is now we walk backwards through every state x visited during that game. So okay, let's talk about one loop in this code, right? So once this entire loop is run, it has to run by 50,000 times. Once this is run, there will be a final state, right? We just finished a game and there will be a final state. That state will have a value. Now what we're trying to do is we will see if we can use that value also to backfill the values of the previous states, right? So we want to try and move backwards, right? So simple idea is, if the position I moved to was good, then the move I made to get there was also good, right? So we update the values of the previous states, and then we train, right? So this is where the magic happens. Um, so far what we've done until here is we've built a state value functions. We have learned via TD0 against a fixed imperfect opponent, right? So the opponent was completely choosing random value. Now, I also, as we proceed, let's also see how the game is being played, right? So I define a function to print states, and then I also show you some sample state, right? So I choose 5. So since we've trained, since we've run this code already, so we have some state values assigned to some certain state, right? So for example, in a scenario where you have x, and o, the state value is 0.5, right? In a scenario like this is a loss, right? Because 0 wins here, that means the agent lost. So the value of the state is 0. We wouldn't want to be in such a state, right? The value of this state is higher than the previous one because Here it is more likely that X wins, right? So there's a gap, as you see, right? So the moment and X is turned, right? So X played one, and let's say zero played, then X played, and then zero played. So there is a high probability of X winning in this state rather than this state, right? So this is what state values mean. So if learning worked as happened, because we've already run the train command, strong position should have high values and losing position should have low values. So then we try and sort the state. Just this is just for demonstration sake. You can skip this code, but this is where we are sorting states based on the value on the values that they have, right? So we choose the we choose the worst states with zero values, and the best states, uh, I display both of them, right? We can display more, but for your reference, in all of these states, we have lost. So 0, 0, 0, or draw. So this is also value 0. We don't want to be in a situation. But here we won, right? So XXX, again XXX, and then here also XXX. So we won, so the state value is 1. Yes. Now, the scenario described in the book is where our agent X learns greedily and it competes against the random O opponent, right? Uh, so let's try and articulate this in the next function, right? So we're playing game. For X, we're choosing move using an epsilon, right? So when we set epsilon equal to 0, there is no more exploration happening. So X is always going to play smartly. And by smartly, I means it is going to exploit the knowledge that it has. So I should rather say wisely, or I don't know. Yeah, basically, it is not going to gamble. It is going to play with the values that it already knows. And for O, we are playing again randomly, right? So there is like O has got no uh, opinion. It just plays random choices. So the likelihood, and then I simulate these games, and I also print the states. But it is obvious to us if we play uh, with if we already know the state functions where we know the probability of win is higher, we are going to play more smartly than our component who's than our opponent who's going to choose random values, right? Who's going to just choose random values from out of nowhere, right? So we are going to have more probabilities of win in a situation where X is taking more informed decision. Um, there will be more win out of the number of games that is played, right? So let's say if I'm playing 1,000 games, and if I collect the number of games in this dictionary, um, X should have more number of wins, right? Eventually, and then this is exactly what is happening here, right? So I'm printing these states also. So let's see here. So this is where the game starts. Let's say one episode starts. So X plays, and then 0 plays. The value function increases. Then X plays. Uh, value function is 0.5 here. And then 0 plays here, then the value function again goes up 0.91, because this time the X can simply put here and the value becomes 1, and the game ends, right? In another situation, X plays here, O plays here, X plays again here, O plays here, uh, and then X plays here, and then you have X playing, eventually X winning again here, right? So you can also print out these states and see how the agent is playing against the opponent, because opponent is completely taking random choices, right? And X is playing much more smartly, right? To be honest. So if let's take a look at the situation where X plays here, then O plays at the bottom, and then X plays here. Then if O was not playing randomly, the next step of O should be here, right? In order to avoid X from winning, but O is just playing randomly, so X also wins in this game, right? So finally, out of the 1,000 games that we played, 879 were win by X, right? This is as we predicted. So this agent wins most game and never explicitly planned a single move, right? We now visualize how the learning happened, right? So what I do is now I train this game for 20,000 episodes, and every 200 episodes, I'm trying to see how many games did X win and how many did it lose, right? Right. So what it does is every 200 games, I'm taking a checkpoint and I'm trying to see how many games were won by X. So wins per 200 game. So as you see, the number oscillate really close to 200, right? It is like in most of the cases. So the number, like if you take the average, it is going to be around 177 or 178. But the idea is that out of the 200 games, every time uh, X wins around 170, 180, right? So more or less with this approach, when X plays smartly and it exploits, does not explore much, it is going to have more wins, right? Cool. Now this is the right time to jump to exercise 1.1 in the book, self play. So what if? So I will quote the book. Suppose instead of playing against a random opponent, the reinforcement learning algorithm described above played against itself, uh, with both sides learning. What do you think would happen in this case? Would it learn a different policy for selecting moves? Obviously, yes. The short answer is yes, because if you play if a smart player is playing against a smart player and both of them are not ready to explore much, um, and if you play tic-tac-toe enough, you will agree that most of the games result in draw when two smart players are playing, and this is exactly what we're going to see. So the environment has become non-stationary, meaning the opponent's behavior is constantly changing as the other player learns and improves, right? So it is not no longer a fixed predictable setup like playing against a random or static opponent. So each agent's policy keep changing while the other is learning, and value estimates also oscillate, right? Cool. So when we define this time we have two value functions, right? So we're collecting value of me, like the main player, and then value of opponent, right? So uh, yeah, so the essence lies in this line. So let's say for any player that is uh, for any player in any given state, the state value will either be 1. In case of draw, it will be 0. If the opponent wins, it will be -1. Right? In all other situations, uh, this line defines the state value, right? So this line should be read as following. So I evaluate this move by assuming the opponent will play to maximize their value. And since whatever makes them happy makes me sad, I take the negative of their value. So what is happening is here is in if the situation is not amongst these three, in all other situations, the state function according to me will be the negative of state function according to the opponent, right? Now we define another function called train self play, this time because we are playing against ourselves, two smart agents competing. um, so we have trajectory, so we take empty list as trajectories and then we append states to them. So X starts again, the game is started by X in the environment tic-tac-toe. uh, when X plays, the state is appended to the trajectory, and then the move is chosen by the function that we've defined above. Same thing goes on for O. And if you will see, these two functions are completely interchangeable in terms of X and O, right? So order of VO and VX changed here. Right, so result rewards are collected. Um, yes. Uh, Discounting factor, we don't need it here because I eventually take gamma to be 1, so we can skip that, right? This is where I define how the agent is going to play, how both the agents are going to play. So we set epsilon equal to 0 for both the agents because this time both the agents are competing against each other, right? So X is also paying smartly and O is also paying smartly, and that they're not going for any exploration. They're going to exploit the knowledge that they have. Again, I publish these results. I show some simulations, and this time it is more interesting to see. So let's take a look at the random game. So this is where X starts, and then O plays here, and then X plays here. So if O is smart enough, this time O should in the next state, O should appear here, and this is exactly what is happening here. So this time O is playing more smartly. It's not taking random moves, right? So it is more likely to result in a draw. So let's take a look at another example. X plays here, O plays here, X plays here again, and then O should come here. Okay, so and then X plays here, and then O tries to maximize it win, but then X is smart enough to play here. So yeah, eventually this also leads to a draw. So this is exactly what we see in a normal situation. Two smart players playing a simple game of tic-tac-toe results mostly in draws. And this is exactly what we will see once we look at the final result of this. Yeah, as you see, out of the 1,000 games that were played, all resulted in draw because both the agents were competing against each other. Right. So in true self play, both agents learn and exploit their own value functions, and the game naturally converges to draw because that's the optimal outcome. Thank you.